Uh, Hello everybody. Give me one more minute to open chat. Okay. Hello. Today I'm back with lectures, and the topic is. I thought the name would be sorting with DP, so I didn't know the name of the technique, and it's just something related to sorting with some strange comparator, but fortunately someone in comments, Dalex, pointed out what is the real name, so it's exchange arguments. And actually today I was also told about a video by Algorithm Life, and I watched it in the morning, and I strongly recommend watching it if you're interested, because it shows you how to prove things. So it's very important. If you don't have a strong math background, then I recommend this video for you. Well, if you want to learn how to prove things correctly, and it's related to today's topic, so I strongly recommend it. Okay, and we will be solving problems from the list in code forces. You can find link to this list in the description below the video. And let's review the technique, the exchange arguments technique. If we are given n items and we should change their order, and possibly then to remove some items, only leave some of them, then we should think what is a good order of them, and sometimes it can be hard, and usually it's enough to solve the problem for n equal to 2. So if we are given 2 items, we should think what should be their order. And if you use this order, this comparison of 2 elements in order to find which one should be earlier, we can use it to order the elements and then apply the dynamic programming to know what is the biggest possible number of items. And let's see how it works with an example. The problem is boxes. There are n boxes, each with some weight and strength or durability. You can choose some subset of boxes and rearrange them in any order you like. Find the maximum possible number of boxes in a tower where the strength of a box must be not smaller than the sum of weights of boxes above. How nice to see you again. Thank you. Yeah, it's good to be back. So I was for some time in USA in various competitions. I didn't win any. And let's move to the problem. Also, please remind me, if I forget about it, to change the title. The title is visible, I think, for you in the top left. It should say, for example, right now, 1 boxes. Привет, but please let's use English. Okay. So we're given a set of boxes in this problem. There are a few boxes. Let's number them. 1, 2, 3, 4. And each has some weight. For example, let's say weight 4 and strength or durability 9. So this is weight of I, and this is strength. So each one has some weight, some strength. And we should choose some of them and put them in some order. For example, maybe it will be, I don't know, 2, then a 4, then a 1, not necessarily all of them, to create a tower of them. And the following must be true. For each box, the strength of a box must be not smaller than the sum of weights of boxes above. So in this case, congrats for GCJ, thank you. But it was some time ago already. So here, so this box must be able to hold the weight of the boxes above in this tower. So S2 must be at least equal to the sum of weights of boxes above. And we can check in this example whether it would be true. S2 is 7 here, and the sum of weights of first and fourth boxes is 4 plus 1, so it would be okay. So this would be 4 plus 1, so 5, and strength is 7, so it's okay. This box wouldn't break. And we are asked whether find the maximum possible number of boxes here. So here the answer would be 3, I think, unless it's possible to take all 4 of them and rearrange them in a good order. I'm not sure. But what is difficult in this problem? This problem is difficult because we can't just do dynamic programming as we would usually do, because we don't know the order of items. So here, if we, for example, know that they must be put in order, let's say from the top 1, 2, 3, 4, then maybe you would put 1 first, then 2, then so on. And if we, for example, consider boxes 1, 2, and 3 so far, 1, 2, and 3 so far, maybe we can put all of them here in this order, but maybe later there will be, maybe all of them have weights like, I don't know, weight 100 and strength, let's say 0, weight 100, strength 100, and weight 100 and strength 200. And then if we have a bunch of boxes that have, let's say, weight 1 and strength, I don't know, 20, and a lot of them, 120 and so on, then we can't use any of them because the weight of boxes above is already 300. So we can only choose some of them or 0. So here, if we know the order, we would in this order do dynamic programming. If some prefix is already considered, then for every number of already used boxes, we would want to know something, and what it would be? It would be the smallest possible weight of total weight of boxes above. So it would be minimum total weight. So if, for example, this is not 100 but 70, then dp of 1 would be 70, dp of 2 would be 170, and of 3 would be 270. Okay, and we can maintain this dynamic programming, and everything would work fine in complexity of n squared. And the technique we learned today is about the first part, that we don't know the order of these items. I'm new in competitive programming. Recommend me a way for training to improve my skills in problem solving. You can ask me between two problems, so then ask again. Please mute the comments from appearing in the videos, Errichto. It's a bit distracting. I think they appear only for a few seconds and they are on the side, so I think it's fine, and I want to enable you asking questions, and I want to encourage it as long as they are about the topic, so I would prefer to keep them. Nice to see you again. Thank you, Pravesh. Okay, back to solving. So, what about the order? As the theory part of the technique says, so here, we should focus on solving a problem for n equal to 2. We should invent some sometimes strange comparator in order to sort the items. For example, maybe we would sort them just by strength, and it will be sometimes trickier. And then after finding this order, we would run the dynamic program. And so let's do that. So there are only two boxes, let's say. Let's name them 1 and 2. And right now, everything is okay if strength of 2 is at least equal to the weight of 1. And when would it be better to swap them? So to put 1 below. When S1 would be at least equal to weight 2. So then it's possible to swap them. So instead, let's think when this ordering is the only possible ordering. So 1 can be above 2. So this is true, but we can't swap them. So instead of this, we would have the opposite of that. So S1 is smaller than weight 2. So then we can swap. Let's actually change the order here. I'm just swapping the sides. And let's combine these two conditions. So S2, I'm summing up these two. S2 plus weight 2 is greater than S1 plus W1. So this is a case when 1 must be above 2 and it's impossible to swap. And so this is how we would solve the problem for n equal to 2. We would just check that. Of course, for n equal to 2, we could just try all the possibilities, but it's not what we can use for the general case. We want to use this comparison in order to know which one should be above, and we want to use that as a comparator for the whole problem. So actually we will write for sort, let's say that there are some points in vector p, maybe in vector, I don't know, a. We would sort a begin, let's say it's a vector, a end. I'm writing what I would write in C++, and here some comparator CMP, and this is this comparator. So it returns for two elements. Maybe this A was a bad idea. Let's call it so vector V. So two elements, A and B, we compare just by checking whether A dot strength plus, so I'm rewriting this, plus A dot, sorry, not A, B. So item 1 is A, item B is 2. So this is B. So we check whether B dot strength plus B dot weight is greater than A dot the same. And this will give us an optimal order of items. Martin, I will answer later after solving the first problem. So this will not always work, because sometimes, very important thing is what you can see here, is that not all comparators are fine. So not every comparator is valid. For example, return, when we sort pairs, return A first smaller than B second is not valid. A comparator is fine if it defines the order in mathematics. The order is, what the name suggests, is the ordering of some elements that doesn't contradict itself. So it satisfies some conditions like transitivity. If A is smaller or equal B and B is smaller or equal C, then A is smaller or equal than C. So here it's about, so if our comparator takes two boxes A and B and it says that A must be above B, so here it would say, comparator would say that A is smaller than B. So this is, comparator returns true if it thinks that A should be earlier than B. But if it also thinks that B is smaller than C for some other box C, but given C and A it would say that C is smaller than A, then it's not a valid comparator. We don't know, then let's say that the ordering it produces is undefined. Actually in C++ it can give you runtime error. What I encountered once in one of my streams. So be careful about your comparators. Here it must be okay, because we can say for each item that its, let's say, quality or priority is just the sum strength plus weight. So here for this item we would say, for this box you would say that its sum, so its priority is 13. Here it would be 10, 3 and 11, and it will just sort them according to these values. So 13 will be first, it's I think it's from biggest values should be first. No, so it returns true if second element is bigger. So if A strength plus A weight is smaller than B dot something. So small values first. So this item will be considered to be in the top always. So the order to consider will be 3, box number 3, then 2, 4, 1. Let me just open this YouTube video on my laptop to see if my face doesn't cover the drawings here. I don't use mouse to draw sketches because it would be terrible. I use a graphical tablet that I bought recently with a pen. So this, I can give you an example of how what I write would look like if I use a mouse. For example, I would write B. This would be B dot strength. I understand that what I write with tablet isn't much prettier, but I hope it's possible to be read. And this is a solution. So first sort using this comparator, and then apply dynamic programming that we talked about first. Okay, and what is the complexity of this solution? Well, we first sort in n log n, and then we apply n² dynamic programming. Also, I've put a bonus here with n up to 100,000, but then it's just a harder problem, and not necessarily it uses this technique. Well, still, you must sort items, but then instead of dynamic programming, you must do something else. Okay, do you guys have any questions right now? And let me answer questions from the top. Thank you for both your efforts and time. You're welcome. I'm glad some people like the streams. I'm new in competitive programming. Recommend me a way for training to improve my skills in problem solving. This question was asked thousands of times. You should just solve problems and like learn new algorithms, read tutorials, editorials, and there's no magic to that. And also you can Google, for example, you can Google incodeforces.com how to train, and you can read a lot of blogs. This I answered. I've always wanted to ask, says Martins too. Some dynamic programming list boxes deadline allow for n-log-n solution, but others don't. Knapsack, edit distance, etc. What is so special about those? It's about some special properties, usually like some greedy solutions working or some function being convex, but there is no general, no general formula for that. And it's very hard, for example, to determine what problems are possible to solve in n square or n-log-n. For example, it's possible to prove that sorting can't be done faster than n-log-n if you only can compare two elements, if you can't do anything else. But other things are very hard to prove like that. Why we will get runtime error? In C++, sort assumes that the comparison, so that the operator smaller than, it assumes that it works, so it doesn't contradict itself. If the operator says that A is smaller than B, then the sort assumes that B can't be smaller than A. And if it does, then something can break. Some assert, let's say, might fail, or something not like less obvious. It won't necessarily be, for example, going out of boundary, but I think it isn't defined. You said we'll do n square after n-log-n sorting, so what have we gained? We solved the problem. Without the sorting part, we can solve it. We only could do n square solution if we know the order. So if, for example, we know that we must put them in order 1, 2, 3, 4, 5, but we can remove some of them. For example, here I gave an example with first 3 boxes having big weights and then a lot of boxes with small weights and strength, and then it's optimal to remove those big boxes. But actually it would be better to put them in some other place. And the sorting gives us an order, and with an order we can do dynamic programming. An English judge to submit for problem 1 and the bonus part. It's awesome that people in the comments provide a lot of new problems, and here Nikolai provided links for first 2 problems, and with Russian statement also the bonus problem. So big thanks to him, and you can follow the links. For example, here in Code Festival you can find the problem we've just talked about, apparently, or something very similar. It's loading for a lot of time. Do I have internet? Okay, I have the internet. So it's just the AdCoder website is quite slow. Yeah, assert breaks in debug mode. Yeah, and without debug mode, it can be just, let's say, undefined behavior. I'm not necessarily sure, but sort assumes that the comparator works. So yeah, here we have a problem with n items and each with some height and power, and apparently it will be equivalent. You can solve that later. Okay, let's move on. Second problem will be harder, but similar. Let me change the title. Problem hero. There is some hero. Here the problem was from Polish contest, so our names are always like Bitek or Bitor, something like that. So here Bitor has H health points initially, and he must defeat n monsters, and is up to 100,000. Each monster deals some damage DI, and after death it drops a health potion that restores some HP points, so some HP, so AI HP. And this HP, your HP, can be above the initial value. For example, if so if your initial HP is 10, and then you defeat someone with DI equal to 2 and the restoration value equal to 5, then initially this damage would drop you to 8, but then this potion would give you 13 because it's plus 5. Okay. Can Vitor choose the order of fights in such a way that his HP never drops below 0? Print no, or print yes with the order of monsters to fight with. And the bonus is n up to 2000, we should maximize the number of defeated monsters. And you can guess already that so the first part is just about sorting. So we'll use our technique to sort sort monsters in a good order, and we'll see whether we could defeat them. Also, it could be used if, for example, the question was what is the minimum possible initial value h so that we would be alive. Then we could binary search this value maybe, and then try the ordering to know the minimum possible one. Or maybe if we know the order, then we will know, for example, if our initial HP is some x, some variable, then we can say that then it will be x plus 5, x minus 7, something like that. And with this, then in constant time, we can say what is the minimal point where we were, and we can in constant time get that h that is minimum possible. But the bonus part is just about adding the dynamic programming like in the first problem. So let's focus on choosing the order, because this is what this lecture is about. Why can't we greedily choose monsters in order of AI minus DI? Well, maybe we can, but the question is, why is it optimal? And actually, a good lesson is to try to find a counterexample for that. So the idea by Mislav is that we should greedily choose monsters in order of AI minus DI. What makes sense? And I will try to give a counterexample because I think it's false, like it isn't correct. So idea, sort by AI minus DI. And I agree that this makes a lot of sense. So the intuition could tell you that. Rohit says maybe DI can be greater than initial HP, so we can't defeat the monster, but we could defeat it if we defeated other monsters and can restore points. Exactly that. So let's say that one monster has DI equal to let's say h is equal to 5, and first monster has DI equal to 6 and AI equal to 1000, some infinity value, and the other has DI equal to I don't know, 2 and AI equal to 4. So starting by this, we would first fight with this monster because it gives a lot of health back, but we can't. So some idea to fix it would be maybe to try to always fight with among monsters that you can fight with. So here initially only this monster is allowed. Choose the one with the biggest value of AI minus DI. But again, we would have to prove its correctness. And if we also, and I think if we also encounter monsters that deal more damage than AI, it might be wrong to do that. But I'm not entirely sure. So we'll try to solve a problem and prove the correctness. And also I repeat that to learn about proving the correctness, I strongly recommend the video by Algorithms Live by Matt Fontaine. So the lecture number 14. I will add the link in the description after the stream. And it will teach you how to prove things and not how to correctly prove things. Okay. So here again, we will try to solve a problem for n equal to 2, but for that I will use some graphical representation, what is often very valuable thing. And what I will do here? Well, we start with some, so this is HP, and this is, let's say, time. We start with some value h, and every monster consists of two parts. He deals some damage to us, and then he gives some HP back. So this is one monster. And maybe the second monster is, I don't know, something like this, something like this. So each of these parts, like two-part segments, is one monster. So here it would be, so here we are after first fight, after second after second fight, and after third part. And the question is, what is a good order? So actually, likely h will not matter here. What we will want to optimize is among these corners in the bottom. So after a monster deals some damage to us, we care only about our minimum possible point, not minimum possible point, minimum achieved point. So it's our minimum HP, like in the whole time span. And we wonder whether this is greater or equal to 0. So actually we can skip h if we just say that this is x. Like let's say we don't know x. Then we want to minimize this distance from the initial HP to the furthest point in the bottom, and we want to check whether it doesn't exceed h. So we change the problem a little bit. We want to choose an order of monsters in such a way that our lowest ever point of our HP is as high as possible. Okay, let me create a new drawing. That's too bad that I can't understand anything because of my bad language. Well, I can do nothing about it, I'm sorry. Oh, sorry, but can you speak slower, please? I'm a newbie and my English is not good. What I think I still talk quite slowly because my English is not that good. And actually I heard from some people that they prefer watching streams later in speed times 2.25, so slightly faster. I think a solution is that you can later watch the video in speed like 0.075. Maybe even it's possible right now here, I'm not sure. So here you can choose speed, slower speed, and you will get back, like you will not be live, you will watch me from minutes ago, but maybe it will help you. Okay. So the question is, what is a better way to order two monsters? So let's say we are at some point, and we wonder whether it's better to put them in this way or let's say this is monster A and this is monster B. So this is B deals damage to us and then restores some health back. And whether this is better or maybe BA better. And let's see. Let's say that this point is just 0. It doesn't matter. So how much to the bottom we go with the first damage? Well, we get minus DA, and here, let me write it here, minus DA is this point, because this is the distance is damage that is done by A. Then we got A back, and then DB again. So this point is here minus DA plus that we restore some points after fighting A, and minus DB. And we are interested only in the minimum of that. So we compare that to the other order, and the other order will be just the same but with opposite indices. So let me just rewrite this, but with B and A swapped. And we wonder what is a good order. And it's very hard to compare these two, because we have a lot of inequalities, possible inequalities. So we, for example, maybe this is the minimum possible value, like maybe this is smaller of the two values, and then we should compare it to DB, and also to this one, what will be equivalent to comparing minus DA with minus DA plus this part, and it becomes very hard to do. And either you can try to like write down these inequalities. For example, maybe like first case will be that minus DA is smaller than this, so minus DA plus AA minus DB. It's also maybe smaller than this, and you can try to get something from these inequalities. And first, maybe you can make some simplification to this expression, because you can notice that minus DA is in both expressions here, so we can say that it's minus DA plus minimum of 0 and the other part here, so this part, and this is similar thing. It doesn't help that much, but maybe then it will be easier to analyze. And either from this you will get some observations or ideas what to assume, what to do. For example, when you compare this term to this term, you will notice that we care about AB minus DB. And actually checking whether this is greater or smaller than 0, so checking whether this is greater or smaller than this expression, has a lot of sense here in our statement. And this is something that we actually can do without any computations here, just something that we can guess. That logically, if you want to find a lot of monsters, it makes sense to first fight those that give you more health than they take. So idea is that maybe first monsters that have AI greater or maybe equal than DI, and only then those with smaller value. So these are monsters that take more damage than they give you back. And we can prove the correctness of this just by thinking whether if there is some monster like this before, so let's say that this is bad monster and this is a good monster. And so I claim that it's okay to first fight good monsters and then bad monsters. Actually, the exact lemma that we should prove is there is an optimal solution where all good problems or good monsters are earlier than all bad monsters. And to prove it, you should consider the opposite case. So maybe some bad monster is before a good monster. It might be trickier to formulate, but then it also must be true that some bad monster must be just before a good monster. So in any string where there is something like good, 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 bad, bad, good, bad, good, bad, bad, there is in particular a place where there is a bad monster just before a good monster. And we can focus on this exact place. And we should say that it's better, like it doesn't hurt us to swap them. It can only be better. And what is the proof of that? Well, if we first fight with a monster that gives us more health, and then fight with a monster that deals more damage that it gives back, then we don't know which of these 2 points are lower. But if we switch the order, so first we fight with this monster that is bad, and then with the other one, then I claim that this situation is worse. Why? Let's focus on this point. So let's say that this is 0 for a moment, and let's say that this level is, let's say, I don't know why. So here, so this monster here, let me use some color. So this is a good monster. Maybe I should choose a green for this. And here it got us to level level Y. And here we have something smaller than Y, because this monster deals Y damage. But first we fought with monster that got us from this level 0 here. So by this distance, we are worse than this first Y. So this is actually Y minus something. And this something is, for the first monster, it's damage minus restoration. So this is worse. And we can do a similar thing for the second monster. So here, if it's initially some, I don't know, Z, then this Z is only smaller. So again, I will write Z minus something, just a different something. Why? Because here in the first case, the first monster helped us first. First monster, good one, so red here, give us some distance up. We gained some health points. And then we got back by D, here, the damage. And here we don't have this boost, this initial boost. So this point must be lower than this point. And if we compare the minimum of the two, and now the minimum of the two where both numbers are decreased, then this is worse situation. So what we proved is that first good monsters, then bad monsters. And this is only the first part, because now we want to focus on good monsters and know how to order them, and do the same for bad monsters. So at the end, our comparator will look something like this. So there is some comparator, let's say CMP, of monsters, let's say A and B, and it will look like this. If A, let's say, is good, and B is bad, then return true, and then if A is bad and B is good, then return false, and so on. So comparator should return true when we think that first element should be earlier than the second one. And then we will write if A is good and B is good, then do something else. So now we want to know how to compare two good monsters. So how to do that? So we now have, okay, let's get back to our computations here, and now we know something. So we know, I think that maybe taking a look at this will be enough. We compared two good monsters, so actually something matching this drawing, and we know that restoration is bigger than, or equal maybe, than damage. And we can maybe see something here thanks to this. So actually we know that, let me change color. This is smaller or greater than 0? Greater equals 0, because A is bigger than D. And similarly this is greater equals 0. And what it means? It means that something positive minus dB must be greater or equal than just minus dB. So I will write that this is smaller than this. And also symmetrically, this minus dB will be smaller than this expression. And what it means is that among these four numbers, only these two matter for the worst minimum. So what I claim is that we should just check which of these two is smaller, minus dA or minus dB, and it will give us the smaller total minimum. Because, for example, if this is, let's say, minus 7 and this is minus 5, then we know that from the inequalities, this is something greater than minus 5, this is something greater than minus 7. So among these four numbers, minus 7 is smallest, no matter what is the AI exactly, as long as the inequality holds, that the restoration is greater than damage. So this is something that gives us the worst case, so our lowest value will be small, so we should choose this one. This is greater minimum, something giving us better worse HP. So we should choose B first when minus dB is greater than minus dA. Actually, we want to know when A should be taken. So A should be taken first when minus dA is greater or equal minus dB. So dA must be smaller equal dB. Then it's okay to take A first. And actually in the comparator, so here we want to say, well, in particular, if A is good and B is good. Comparator should return true only if we think that A must be earlier than B. So comparator is something that returns whether A is smaller than B. So this is the idea for comparators in C++. So here, when there is equality, we don't care which one is earlier. Because then both the A is smaller or equal than the B and the other way around, because there will be equality here. We want A to be earlier for sure when the A is smaller than the B. So here we would say return A dot damage. How was it? Smaller than B dot damage. And this is a correct comparator now. Also, we must compare to bad monsters, so those that deal more damage than they give back. And either we can repeat the computations or our analysis observations, or we can say that this is symmetric situation just from the end. Because actually, if you have some, let's say that for some reason we know the optimal subset of monsters, and we put them in some order, so first good monsters, then bad monsters, then actually we can also say that well, we know the initial age, so we know the final age, because we can just, no matter the order of monsters, it will be the same, just the sum of all restoration minus the sum of all damage, and we can apply the same process from the end. It's the same thing. So we only care about some global minimum that will not necessarily be here. Possibly here we have a monster like that, and possibly this will be smaller. So from this symmetricality or symmetry, we'll know that for bad monsters, so here we compared by this by damage here, whether this damage is smaller than this damage. From the end, it will compare by something symmetric, but here it's the second part of the. So this is the description of one monster. It deals damage and it gives us restoration. So something symmetric from the right will be restoration, not damage. So for monsters, we will compare A restoration with B restoration. And if I'm not mistaken, here it will be greater, because it's opposite. I'm not entirely sure, maybe it's smaller, so I would have to think for a minute, but I think this is a good comparator for two bad monsters. And this will give us a good order, so then we can say what is, for example, the minimum possible initial HP, so that we would be alive for the whole time. And also we can do the bonus problem just by applying the same dynamic programming as in the first problem. N up to 2000 to maximize the number of defeated monsters. So just start with this comparator and then do dynamic programming with so the number of defeated monsters and what we should maximize or minimize here. Well, our current HP. We can't do that before the sort because we don't know the good order of defeating monsters. So possibly the first monster wouldn't be possible to defeat first, but instead if we put some good monsters first, then we can defeat everybody. So we sort to have the ordering, and then we do this dynamic programming that has memory linear and complexity and square. And the value in DNP is after defeating this many monsters in prefix considered so far, what is the maximum possible current HP? Questions now? So Sai Hemant, I think, provided a good solution. Yeah, sort all good monsters with increasing the I first, then sort all bad monsters in decreasing the I. Does it matter how we sort bad monsters? Yes, it does. So similarly how we gave counterexamples for some ordering of monsters in general, you can try to find, for example, you can try a solution where you don't sort maybe bad monsters, and it's a good practice for you to try to find a counterexample for that. We can sort monsters with lower damage first, then if there are two monsters having same damage, then make the largest restoration first. Does this comparator works? I don't think so. So maybe so I don't want to again try to find a counterexample, trying to find it yourself, or maybe someone from the audience will manage to find it. But yeah, you should, if you want to find a counterexample for something, likely n equal to 2 will be enough, sometimes maybe n equal to 3, and just try to find such two monsters and the initial value h that your ordering will not be good, so it will not allow to defeat both, while the opposite would work. So here I would try, if you want to first sort by the damage, maybe n equal to 3 will be enough, because we know from a correct solution that we know now that good monsters should be first. So maybe something like make your sorting put a bad monster first that deals some damage and then gives no restoration back, and try to find a counterexample. Can you provide some more related problems which I can actually submit on some judge, prefer code forces, see whether what I coded covers all test cases or not? As I said, scroll down to comments and you will find a lot of problems there. In particular, Nikolai provided links to two first problems with English statements for Code Festival and ICPC functions. And you can submit there. Okay, and if you have some more questions, do ask them now, and we'll then move to the next problem. And what is the next problem, if you don't have questions? It's from Polish Olympiad. I don't know which one. I tried to find it today in the morning and I couldn't. Maybe I will find it later and update the blog, so you would have a link. But it looks more complicated, and it will turn out that our technique can solve it. Farmcraft from Polish Olympiad in Informatics. You're given a rooted tree with size 100,000. You are in the root currently and you move along the edges. Moving along an edge takes 1 minute. You want to visit all vertices and get back to the root as fast as possible. What takes exactly 2 times n-1 minutes? I will explain that in a minute. When we visit vertex V for the first time, the countdown is started there, and after AV minutes, that vertex will be ready. We want to minimize the moment when all vertices are ready. When will it happen? So there is a rooted tree. and we want to visit all vertices, so it will be a walk. For example, maybe the following one. First to this vertex from the root, then to this child, back to the root, this child of the root, something like that. In the sentence you want to get back to the root as fast as possible means that when you enter a subtree, you want to visit everything in the bottom here and only then go up from here. And this way, every edge, so there are n-1 edges, and every edge you will go exactly twice. And this is why 2 times n-1. Because for every edge, exactly once you will enter this edge and go down, then maybe move along its subtree, and then back. So this is the minimum possible time. And if you instead do something suboptimal, for example, from root move to this grandchild, then move again to root, then this child to root, and then again this grandchild, then it isn't optimal, because this edge we went 4 times. So every optimal walk, meaning as fast as possible, takes exactly this time, and each edge is covered exactly twice. Okay, what happens? When we visit vertex V for the first time, the countdown is started there, and after AV minutes, that vertex will be ready. So, for example, if there is only a root and a few children, let's say that this AV, so let's say that children are numbered 1 to 3, A1 is 7 maybe, A2 is 5, and this is A3 is 10. So what happens if we visit them from left to right? So something like this. So at moment t equal to 1, we will visit this vertex. Let's say that so the countdown is started there. So at moment t equal to 8, first vertex will be like the countdown will be ready. Then we visit this vertex at moment t equal to 3. So this was equal to 1 and this will be equal to 5. So this is the moment when we for the first time get to this vertex. So at moment 3 we get to this vertex, countdown lasts 5 minutes or seconds. So vertex 2 will be ready at t equal to 8 as well. And vertex 3 will be ready at t equal to 5. 5 is when the countdown is started, and 10 is the length, the duration. So t equal to 15. So we care about the maximum of these times. So it would be here 15. So when all vertices are ready. And we want to minimize this value. And here you can guess that it's better to first go to this vertex with big countdown duration. So if we first go here, so at t equal to 1, we get here, then at moment 11, this countdown will be ready. Then I think it's good to visit this child at t equal to 3, so it will be ready at 10, and this I think will be ready at 10 as well. So then maximum of this 3 would be 11, so it's better time than 15. So if there is only a root and some children, then it makes sense that we should sort them by their AV value and visit them from the biggest one. And this would work, but things get trickier when the tree looks more complicated. So maybe there are a few children of a root, but they also have some subtrees. So some idea is that Maybe we should first go to a child where in its subtree there is, so in every subtree, for example, we start in a root and we wonder which of the three children we should go to first. So maybe we, in each of the subtrees, we would find the maximum value AV that is there, and we would go to the child with the biggest of those values. You can guess a few things like that, but none of that would be correct. Like, it's more complicated than that, and we should do some simple maths. So as usually, we'll focus on case n equal to 2. What doesn't mean that the size of tree is 2. It just means that from a vertex we decide between two children. We just want to know which of the two children we should visit first, and we would do that, let's say, in every vertex. Here we also decide between these two children. And what is important, what comes from the statement actually, is that our walk should be as fast as possible. And if that's the case, in every subtree, for example here, there's this subtree. When we enter it, no matter how we choose the order of children inside, the time needed to go and cover all the subtree is always the same. It will be 2 times the number of edges in the subtree. So we know that here, if we first go to this vertex and it has 1, 2, 3, 4, 5 edges, then we will cover it for some time, and after time 2 times edges, so here it would be 10, we will be back here. And so this is one case, this is one observation, and the other is just something that comes from experience, that in rooted trees, in problems about rooted trees with some, if it's possible, we often should do dynamic programming from bottom up. And here it's possible to be done. And if you had this idea, it was like good intuition. So for every subtree, we will know dp of this subtree, dp of, let's say, vertex v. And it would mean, so when we go for the other part of the tree first, but if we are here at moment t equal to 0, let's say, then what is the optimal way to go inside this subtree and to get back to the root? So actually it's the same problem as the whole problem. We can say that for a moment we can assume that this is the input and we just want to know the answer. dp of v will tell us if we choose the order here optimally, well, when the latest of countdowns will finish here. And if we know that for every subtree, so here we would know it for this subtree and for this subtree. So let's say that left subtree is A and right is B. So we know what we know. We know dp of A, we know dp of B, we also know the size of A and size of B. Let's say that, because it's easy to count, so let's say that size is the number of edges. So here size of this would be 5. And we want to know dp in root. So either we will choose first A and then B. Let me see. Questions. Can we start by maximum sum of path from root to leaf? Maybe it's a reasonable idea. I think it won't be correct, but as always, you would have to prove that. And here I think what you should do instead is try to find a counterexample. maybe not the sum, but the maximum ready time of nodes in the path from root to leaf. Intuition. Yeah, like, I agree that this intuition makes sense. It's more complicated than that, because it will turn out that the size of subtree is also important. So, well, after the stream, try to find counterexamples. It will teach you a lot. So you will just then, during contests, be able to find a counterexample for your idea, and instead of implementing something wrong, you will find a counterexample, and you will spend time thinking about a correct solution instead of implementing a wrong one. Okay, what we do here. If we choose A first, then what will be the total answer? Well, at t equal to 0 we are here, so at t equal to 1 we are here, and so the answer from this subtree will be 1 plus dpa, because it takes us 1 minute to get here. So we go here, then we get back to B. At what time? Well, it takes 1 minute to go here, 1 minute to go here, then size of subtree A times 2 to get around here, so 2 times SA, plus then from this child we go back to root and then to the other child, so plus 2, and we are interested in the maximum of that. Well, and here plus dp of b. And we compare that to, well, the other possible order, max of 1 plus dp of b, and this thing. So 1 plus 2, let me change to just, well, let me leave it. 2 times sb plus 2 plus dpa. Okay, and the question is, which one is better? So one thing that sometimes you can do, for example, you can do here, is just, instead of figuring out how to sort it exactly, so for example, maybe from this we'll get that we should sort by dp of a plus size of subtree, something like that, or minus. But actually, it's possible to just write in comparator the comparison of these two values. So maybe it's okay to compare the maximum of this. So in comparator that gets a and b, maybe we should just check if this maximum is smaller than this maximum. It's a bit dangerous, and sometimes it will work, sometimes it will not. For example, in problems about monsters, you could just take these two monsters and check what order would be better. And the question is whether... so I think there it would also work, and only later we will see an example where it doesn't work. Because the question is whether the other elements matter here. So I think this is the simplest explanation. And here I said earlier that the comparator possibly is not valid. If, for example, it says that E is smaller than B and B is smaller than A, then comparator is invalid. Or if A is smaller than B, smaller than C, smaller than A again, then it's also invalid. And the question is whether a comparator would be correct for comparing these two expressions. For this case, and I think also for monsters, it would work. It's hard to prove, but well, you can guess and just try to submit and see if you get accepted, or test in your own machine with some brute force. But to prove that it's okay and it makes sense to compare by that, we must do the observations that would anyway give us a good simple comparator. And let's try to do that. So here we see that this long expression is for sure bigger than this one. The same here, so this long expression is bigger than this one. So among these four elements, like we now want to find out what is, let's say, what is worst among these two. So which maximum is bigger? Instead of say, actually we want to find the smaller one to minimize the answer, but for a moment let's try to find the worst one. So we want to find the one giving bigger maximum. So among these four values, then we want to find the biggest one, the single biggest one. And if we want to do that, since this is bigger than this smaller one, and this long expression is bigger than this one, it's enough to just compare these two things. Because one of them will be the biggest value of the all four. What it means is, it means that we can forget about these two and just compare using this 3 plus 2 times SA plus DPB, whether it's smaller than 3 plus 2SB plus DP of A. We can forget about plus 3 here. Right now still it doesn't look like something that is for sure a good comparator, but you can use it and it will work. Actually it will work because you can change that simply by moving dp of b to the right side and dp of a to the left side, and you would get 2 times SA minus dpa smaller than 2 times SB minus dpb. So actually for every child here you say that it has some priority. Again, A has this priority, 2 times size of subtree minus dp, and you sort by that, smallest one being first, I think, maybe last. Does it make sense? If something has big value of dp, then it should be early, because we must enter there first. Yeah, it makes sense. So if I didn't make a mistake, because of course possibly I made a typo here somewhere, if I didn't make a mistake, then this is a good comparator. So what is a solution? Solution is to do dynamic programming from bottom up, and every time we are in some vertex and we want to order its children, we should sort them in this order and then say that we visit them in this order from this vertex, and from this simply we get dp in this vertex. We do the linear thing described here. So it's trivial to just say, if we know the order, then we say when exactly we enter every vertex, and if we know it's dp, then we can simply linearly compute the maximum. And that's it. Do you guys have questions? Also, in the meantime, I will say some announcements and self-advertisement. If you are more comfortable watching on Twitch instead of YouTube, you can watch me there on Twitch TV/Errichto. Actually, here in the chat, sometimes you are able to see someone from Twitch. So hello, Twitch. Just the disadvantage there is that you can't adjust the resolution, so you must watch in resolution I'm streaming in, what is 1080p. Sadly, so YouTube is, if you need smaller resolution because your internet isn't so good, then YouTube is a better place, or if you're more comfortable with YouTube. And also, what you can see in the description, I think, of the video, and also here in Codeforces, is link to my Facebook page, facebook.com/Errichto, where I just sometimes put news about contests or my thoughts or just simple tricks, problems that I liked. And also make sure, if you enjoy this stream, if you like what I'm doing, please subscribe to the channel and like the video, because it helps me in growing the channel, and then the video and all my videos are recommended to more people on YouTube, so thank you a lot for that. How DP and sorting is connected? Well, it isn't connected. I'm just saying that in case of problems we're doing today, the connection is that DP you can apply only if you know the order. So maybe I will ask you a question. Are you asking about this problem about a tree, or about previous problems, or generally? Because generally sorting and DP aren't connected very much. Will you be streaming in the next contest? What do you mean, the next contest? So I don't stream contests live. I never did. For example, Petr Mitrichev records himself competing, but I think for me it would be less valuable, because I'm simply worse in competitive programming. I can't do that well. So for example, I can't explain and at the same time do well. But the next stream will be on Tuesday, maybe. I will see, and it will be part 2 of today's stream, because there are a lot of problems left. And the next one will be 4. Also, you didn't remind me that I should change the title, so it was 2 Hero for the whole time, and it should be 3 Farmcraft. Streaming live if a contest would open the Pandora's box of cheating. No, yeah, it's impossible to stream live during a contest, unless all participants don't have internet access, what is possible only in some on-site competitions. Previous problem. So, tree problem or a problem before that? So, regarding the tree problem, we want to do dynamic from bottom to up, but at every moment, so we are at some vertex and we already know dynamic programming for its children. Then the question is how to compute this dynamic programming value for the vertex. To know, so in this vertex and all its subtree, to know the optimal time, so when the last vertex will be ready, we should know in what order we should visit the children. And for that we need the sort with a good comparator. And if you're asking about previous problems, where sorting allowed us to do dynamic programming, because dynamic programming we required some order of elements. Can we retrace the answer for the tree problem? So you're asking whether we can retrace, meaning to know in which order we visit children? If yes, then the answer is true, because for every vertex we know the order, we can remember that. And if you know, for example, that for root the order will be 2, 5, 10, for vertex 2 it will be 6, 7, and so on, then you can just do DFS, for example, and use this order. The next problem will be 4. That is pretty good proportion. Okay. Let me make some. So I will tell you a problem and I will give you a minute. Think about it while I take some light, because it's getting darker here and because the only thing that lights up my face is my monitor. That is quite bright right now, and if I turn the brightness down, then it will be very hard to see my face. And the problem comes from Google CodeGen finals, so you can find it in the internet. Pretty good proportion. You're given a binary string of length n and up to 100,000 and a real value r between 0 and 1. Find a substring where the ratio of ones is as close to r as possible. For example, if the string is 01010 and r is equal to 0.7, then I think the best substring will be this one, because the ratio of ones is 0.6666. Like 2 divided by 3 is the percentage of ones that are here, and it's quite close to given r. And the question is, for given binary string, find the substring with ratio as close to r as possible. So try to think about it for a minute. Siema Piotrek, but please let's talk English other than that. Try to think about the solution and let me get some lamp. Somebody suggested divide and conquer. I think it will be possible, and I think we can get complexity n log square here with this idea. And so this isn't my intended solution, because I want to obviously use the technique that we talk about today. So just I will briefly say how it could be solved with divide and conquer. So we have some string. So we split it into halves. And now we want to consider substrings going through the half, through the middle, and then run recursively for every half. So here, for every suffix of the left part and for every prefix of the right part, we'll do something, and we'll try to combine that. And what to do now? So for every here suffix, we know the number of ones, let's say that it's a, and the size b, or maybe s, it will be the size. Here, so it will be some AI, SI. Here it will be also some AJ, SJ. And the question is whether after, for example, sorting it, maybe by this ratio or something, whether we can, so then for every, for example, prefix here, we will want to know the best possible suffix here that matches this prefix. Actually, I think solving this problem to the end requires my solution anyway, so the solution that I want to tell you. So I don't see how to finish that otherwise, like in some other way. So let's remove that. Actually, I said that I want this technique to be used, but what I also said here is a warning. Not all problems here use the described technique. I think it's a good lesson to see some similar problems and understand when it's possible to use some algorithm or technique. So actually this problem is also maybe about some sorting, but actually it will not use the technique from today's. Why? Because in other problems we had some items that we want to put in a good order, that we can rearrange. For example, in the tree problem, we could choose the order of visiting children. In the two first problems, we just had an items and we were able to reorder them. Here it isn't the case, so even though there will be some sorting, it will not be about like the technique solving for n equal to 2. Finding maximum subarray sum in array. Well, if you just want to apply that algorithm for maximum subarray, you will find the whole sequence. If you want to do something else, then like I don't know how you would adjust that algorithm. So that algorithm is called what? Something starting with K. I think it's K something. Cadence algorithm, if someone wants to check it out later. It's a quite basic algorithm that people learn quite early when they learn algorithms. So it's something that works for a sequence of negative and positive numbers where we want to find the subarray with maximum value. Yeah, I understand that possibly you wrote quite fast cadence, but there is unfortunately some delay, like, I don't know, 10-15 seconds. For example, you can see that I'm typing hello right now, and you will be able to, I think, see it in chat much earlier than I talk about it. I'm not sure it's working here. Maybe I've just spammed the chat. Okay. Anyway. So I don't know how to use cadence algorithm, unless we'll use some other technique that I can mention later. But actually, you should remember that choosing an interval is often equivalent to choosing some prefix, some other prefix, and subtracting them. For example, this is something that is used to do, for example, if you are given a sequence of numbers and we have many queries about the sum of numbers in some intervals, what we should do is we should compute prefix sums. So prefix here minus prefix here will be the sum here. So after we compute prefix sums, in constant time we know the sum of numbers here. And it's often a good idea where we talk about some subintervals, and we'll do the same here. So we have some binary string. What we know for every prefix? Well, we know its length. Here it would be 6. And we know the number of ones. And this is all the info we should need. Alternatively, so this is length, and this is the number of ones. Alternatively, we can count the number of zeros and the number of ones, and it would also be enough, because the sum would be length, but well, it doesn't matter much. Okay, so let's say that this is some L, I, and AI. And what does it mean for us to choose some subinterval? For example, this subinterval will be some longer prefix minus shorter prefix. So actually the the problem boils down to, for every prefix we compute some, we know its length and the number of ones, so we have those pairs li, ai, and we want to choose some two of them, so it will be this prefix in this case and this prefix. So let's say that it will be I and j, and then the ratio will be the number of ones, so aj minus ai, divided by the length, so lj minus li, and we want this to be as close to r as possible. For a moment, let's solve a simpler problem. Let's try to find a substring that has exactly this r. Sometimes it's good, when we have a problem that is complicated, it's good to solve some simpler version of that. Instead of trying to find a substring that is very close to r, let's try to find a substring that has exactly r. And let's just output yes or no. And for a moment, let's forget about the precision errors. So, well, generally in this problem, let's not care about it, because this is not what it's about. So the question is whether we can obtain something like this. So whether we can choose a pair of indices i and j, satisfying this equation. We can transform that a little bit. We would get aj minus ai is equal to r times this. So aj minus ai equal to r lj minus r li. So let me get one index on one side and the other index on the other side. It's often useful. So aj minus r lj is equal to ai minus r li. We want to find a pair of indices satisfying this equality, and then it becomes easy because we just so for every number we know this value, a minus r times l. So we have a bunch of values and we just ask whether some two values are equal. Easy. Okay, and what about getting as close to r as possible? Well, some idea might be to just compute these values and choose two values that are as close to each other as possible. I'm not sure if it's correct. If it is, then, well, we would have to prove it. But what I want to show you is some nice interpretation of that. It helps solving a bunch of problems. Let me open new page. I already said, I think at least twice during my streams, that if you have a bunch of pairs in the input, and here this is what we have pairs LA, we can interpret them as points or maybe intervals, but often as points in the two-dimensional grid. So I prefer black color. So we have a bunch of points. So let's say that here it's L, here it's I. So we have a bunch of points here. And what is this ratio? So the ratio is aj minus ai divided by the difference of elves. So aj minus ai divided by this. And if you know something about geometry or maths, you should realize what this ratio is for 2 points. It's the difference of heights minus the difference of x's. So this is slope of this line connecting the 2 points. So actually the problem is, given a bunch of points, find 2 points such that their slope is as close to r as possible. And what we did already is try to find 2 points that have slope exactly equal to r. So let's say that this is slope exactly r. Then what we did, now let me switch colors, is we sorted points in this order. So it was, I think, first, second, third, fourth, 5, and now I'm not sure, it's hard to say here, but maybe 6 and 7. And so we didn't sort. We tried to, well, maybe we did. Sorting by this would be equivalent to sorting by this value, aj minus rlj. And we just tried to see if some 2 points have equal value, same value. And here, if we sort in this order, then to get 2 points that have slope very similar to r, close to r, then we should just try 2 adjacent points. For example, so because we sort by this direction, for example, this is slope exactly r. And if this is like the next point in this direction, then what we should do is we should consider pair 5, 6 as a valid pair, like as a pair that maybe is a solution. So actually, of course, I'm not here giving you a whole proof, because we would have to put some computations here, some simple maths. But the solution is sort points in this direction. So actually sort them by this value, aj minus rlj. This is equivalent to sorting in this direction. And then try every 2 adjacent points. Just in constant time we know what is the ratio and we compare that with r. So as you see, we didn't use that technique, but I thought that it's still somehow related, and I think it's a good idea to put some problems that are not about the technique, because otherwise we'll just think that all problems about sorting are suddenly like require this technique, and it isn't true. Okay, so we solved the problem, and it's from Google Code Jam Finals, so it's quite hard. Maybe I'm not sure how quickly people solved it, so I don't remember that. But well, if with right interpretation, a problem isn't that hard sometimes. Okay. There are quite a few problems left. I'm sure I will not solve all of them, but soon I will be finishing this stream. So maybe one more problem. So there's no DP right. Yes, that's right, Rohit. Here it was just about sort and checking every 2 adjacent points after sorting like this. So we had this way we got linear number of candidates of substrings, but each we can check in constant time what is its ratio. So the two important parts were, first, remember that interval is the difference of 2 prefixes. For example, if we care about the sum of elements, but it isn't true when we care about the maximum element in interval. So only some operations, only some problems can be done like this. If you are asked about maximum in some interval, we can say that it's prefix minus other prefix. I think that there is a name for functions that have this property, but I don't know how to call it. Anyway, the sum works because you can subtract bigger sum minus smaller sum, and you will get the sum here, but with maximum it will not work. Change title. Thank you. I will change when I'm starting any problem. In the problem for after sorting, we choose the best pair. Yes, that's right. Also, maybe some of you understand the issue that someone pointed out in Codeforces comments that well, when I Google Central European Summertime, it doesn't show my time. So here you can see my time. It's 6:48. But I can Google time zone Poland, and it tells me Central European Standard Time. So it's the same thing. So here I see +1, so I guess that it's about summer and winter time. But is it called like there is Central European Standard Time that doesn't have this +1 then? So there are two CEST times. So I would appreciate understanding this when I post info about time in the future, because somebody thought that the time is different. And let me think what problem is good as the next one. I would solve problem 5, but it's related to problem 6. And I think I don't have enough time for both. So maybe something else. We can talk a little bit about problem 9. So either problem 9, that is like simple short thing. I can talk a little bit about it, but actually I can't prove something there. I'm not sure how to do it. And there is a bonus with very hard problem. And or we can solve some problems given by Dalex. So I saw second and third problems. So third one I don't want to solve now because I don't know how to solve it. So I would have to spend some time. For example, this one is fine. It's problem I think similar to the first two problems. It's very standard for this technique. So tell me, what do you think? My guess is that maybe, for example, this problem is very good for you to try to solve in home, because it's similar to the easy standard problems. Let's see what else we have here. One more problem. It doesn't look very easy. It's too long of a statement. So what do you guys think? Maybe you can use time and date. I can use, of course, but still I would want to be able to say it's this time in this time zone, and some people should understand it without going to time zone. Also, eventually my streams will be later. So somebody asked about it, I think in Discord. So also check out Discord channel, link in the description. Whether streams can be later, I think he lives in USA, and for him streams happen at like 5 AM. Eventually I want to do them, for example, starting now, like 4 PM for Poland. Just not now because of responsibilities, let's say, and also a small apartment, and I don't live alone, so I'm a bit dependent on other things. DP optimization like DNC with exchange arguments. So this is a question about a solution for one of the problems, or what? I vote for no time for dragons. Okay, so if others agree, we can solve no time for dragons. So the problem posted by Dalex. And while you think and maybe vote, let me read the statement again. So there are n dragons. We have an army and we're asked about the minimal number of soldiers that is sufficient to kill all the dragons. So it will be similar to problem about monsters, where I said that we could binary search, or maybe even just say what is the minimum required initial HP to survive. And here we have n dragons. Every dragon, for every dragon, we need an army of AI soldiers to defeat it, and among them BI will be killed. So we have to need, at this moment when we fight this dragon, we need at least this number, and some number of them will be killed. So like if some dragon kills a lot of guys, likely he should be late, because if we lose a lot of guys early, then we will not be able to fight other dragons. And on the other hand, if somebody requires a lot of soldiers, then he should also be early. So my intuition, my guess is that we should sort by the sum, A plus B. This is what I would guess, but of course if we solve it, we'll try to do some drawings or computations. Maybe a problem that involves that, but I don't have a problem that involves DNC and exchange arguments. Why isn't 9 just sorting lexicographically and concatenating maximum first? Well, either prove that or find a counterexample. And the answer will be that it's not correct, and you should find a counterexample. Okay, so we will solve no time for dragons. There are no people that say we shouldn't. So let me change the title. Daleks, no time for dragons. Okay. So okay, let's do some drawings. Let's say there are 2 dragons. What were the names? So every dragon requires at least AI and kills BI. So for you, I will leave actually solving a problem in a standard way, and what I will do instead is I will try to show you that this problem is the same problem as, I think, Hero. Because let's remember in Hero, can there be 2 different correct comparators for a single problem? Yes, there can be, but most likely they will always return the same thing, because just some expressions you can write in a few different ways. For example, you can, I don't know, AI smaller than BI, it's equivalent to saying, for example, max AI, comma AI minus 5 smaller than max BI, sorry, it should be, here I meant AJ, and here AJ minus 1, for example. Just here, of course, it's trivial to see that maximum of these 2 is equal to this, and maximum of these 2 is this, so it's just equivalent to comparing AI and AJ. And we saw some examples where it was more complicated, but still those complicated cases, maybe we have something here, no we don't, those complicated cases where we compared maximum of minus DI, comma, minus DA plus DB something, it turned out to be equivalent to something simpler. So yeah, there are many ways to write the same comparator. Just it's sometimes not obvious. Okay, so did I change title? Yes. Okay, let's forget that. In problem about hero, so in problem hero, we had, so every time we got down by some value and then up by some value. So it was, I think, then D damage and A restoration. Actually, instead of A, let's say that restoration is R. So what I say is that this is the same problem, because monster with these parameters just means that we should, when we fight it, have at least D HP, and also it kills some HP, because it kills D minus Ri. Like this is the amount by which we go down after fighting this monster. And so this way, from hero we can get to this problem, and the other way around is should be as simple as that. It's like equally simple. Requires AI, what means that in hero we would, so it means that first it deals AI damage, but then it gives us back some number of soldiers here, such that this distance is Bi. So here the restoration would be AI minus Bi. And we can do that even without any drawings or computations. Just by looking at the problem, we can say that, okay, if he needs an army of AI soldiers and Bi will be killed, we can just say that he kills AI soldiers and then AI minus Bi are restored. And then it's the same problem. And so for you, as let's say homework, I leave trying to solve it without these observations. So just focus on this description, that it requires this amount, kills this amount, and try to write a comparator for that without thinking about hero problem. So either do some drawings and think whether if it's possible to do some drawings, or just do maths. Say that if we put monster A before monster B, then we need at least this number of soldiers, and otherwise this number of soldiers. And with this, I'm finishing this lecture. The next one, so the next one will be in a few days, maybe on Tuesday. I will let you know in, I guess, Facebook Codeforces and in my YouTube channel when the video is, when you visit my YouTube channel, when the next video is scheduled, you can see it here. Okay, and it will be part 2 of this topic. And I guess then the next stream will be in maybe a week from now, and this time I will get back to just solving problems during a stream, because also it's easier for me and I don't have to prepare so much, because of course gathering the problems here requires some effort, and just solving problems during a stream is easier. So I will think whether it will be again some problems from Polish National Olympiad, or maybe from Codeforces. If you have some suggestions, let me know by Facebook Errichto or in Discord. So thank you for watching. Would you recommend a few books for beginners? Thanks for the lecture. As usually, I recommend Handbook Programming Codeforces. I recommend this PDF book by PLIC or PLK. So Competitive Programmers Handbook. It's free, you can see it in the internet. Some COI problems, probably, maybe. I think it's a fine idea. Can you please share any blog for this topic? For which topic? If you are asking about our today's topic, then you can see my blog. And I'm not aware about any other blog about that, except for the video I told you about. So what I recommend is Algorithms Live, exchange arguments. And here you will learn about proving correctness of especially some greedy algorithms, but it's related to the topic that we covered today. It's not the same thing, but it's related, and it teaches you a lot. So thank you again, subscribe, like the video, and see you next time. Bye bye.